Okay, so let's start with your question.
Okay, so when like in the last week's lecture, you said like uh absolute square of C1 square plus absolute square of C2 square is equals to 1, and that is like part of three dimension because you break it up into real and imaginary part. But I'm not completely sure why it will be three-dimensional instead of like two-dimensional.
Oh, right. So, I mean, this was just a side comment. It's not important
Okay.
for the whole thing, but let me explain. So I said that acha, Tasnim. Sorry. Yeah, there's also another person called Tasnim in this class. Ador, acha, I will send you a. Can you hear me?
Yes, sir.
I will send you an invitation to the class. That way, you'll be able to join the class without asking for permission. Okay.
Okay, sir.
Acha. So, welcome to Tasnim Anzumador, who is. I'd completely forgotten that I had also signed the same papers to him, so it'll be good for him to join the group. So here there's someone else, Rafa. She is joining us from the U.S., Ohio, I believe, right? Uh,
Yes.
Worcester College, Ohio. So yeah, interesting. Coincidentally, both of you guys have the name Tasnim in your name. So okay, so Ralpha was asking a question related to something I said in the last lecture. So another thing you can do, the other, is that you can go to the Slack, and we have done 2 lectures, and you can, and there are links to the lectures on Slack. If you go scroll up,
Yes, sir. I've
yeah,
seen that.
yeah. So make sure you watch those lectures, and then if you have any questions, we can discuss those. Okay.
Okay, sir.
Okay. So the question that Ralph asked was that suppose that we have uh, a state psi, which is a state of a qubit. A qubit is a two-dimensional quantum system. It is the generalization of the word bit for quantum bit. Okay, so a, a general state of a qubit can be written as the linear combination of the zero state and one state. Okay, so the zero state and the one state, they form the orthonormal basis. Okay. So for example, 0 0, the and 1 1, this will give me 1. But 0 1 1 0 will give me 0. Okay. Now we want psi to be normalized as well. That means that we want psi, the bracket of psi, to be 1. So this means that C1 mod squared plus C2 mod squared have to be 1. And I said that this implies that superficially that the state space of the qubit is a three-dimensional sphere S3. Superficially, okay? And Rafa wanted to know how that is the case. Well, the way it's a case is that suppose I write C as a complex number, so I can write C as, say, x1 plus ix2, where x1 and x2 themselves are real numbers, right? And I can write, say, C2 as x3 plus I x4, where x3, x4 are also real numbers. Okay? Then C1 squared plus C2 squared, the mod squared, equals to 1. This equation if we express it in terms of x's, this becomes x1 squared plus x2 squared plus x3 squared plus x4 squared equals to 1. Okay, so here what we see is that we have 4 variables, x1, x2, x3, x4, and there's one constraint. So if I were to plot the surface that is satisfied by this constraint in this 4-dimensional space, so if I have a space where it's a 4-dimensional space, so the axes are x1, x2, x3, and there's an x4 axis, then this is a 4-dimensional space. And if there's one equation, then that 4-dimensional space specifies a 3-dimensional subspace in that 4-dimensional space, right? And my claim is that this equation defines a 3-dimensional sphere. And to motivate this, let's look at the circle. A circle is a 1-dimensional surface, quote-unquote surface, in a 2-dimensional space. So if I take x1, x2, so it's a 2-dimensional surface, and I want to look at all the points that satisfy this equation, then what, when x is 1, x2 has to be 0. Suppose x is 1 here, and x2 is 1 here, x2 is minus 1 here, x1 is minus 1 here. So it should be clear that this equation is tracing out these set of points. Is that clear to you, Rafa?
Yeah, now it's clear to me.
Yeah. So, the way to see it is to actually, okay, this circle has radius 1. So we can say, okay, x, and suppose that for a particular point, say this angle is theta, then we can say x1 is 1 times cosine of theta. x2 is then sine of theta. And then, we can then verify this is the intrinsic parametrization. This is a parametric. Then we can write this as x1 squared plus x2 squared, the left-hand side of this equation, and we see that we get cosine squared plus sine squared, and of course it's automatically equal to 1. So now, if I do the same thing, but I do it in 3 dimensions, so we have, say this is x, this is y, and this is z. And then suppose we are looking at an equation which is x squared plus y squared plus z squared equals to 1. Then if x is 1, then all the others have to be 0. If y is 1, then all the others have to be 0. If z is 1, all the others have to be 0, right? And and then we can just you can verify that this is a circle. So it's not a very good circle. And then we can because this has radius 1, we can parametrize the circle again by a set of two angles. So here theta was the intrinsic coordinate of the circle. Okay, meaning that it didn't have to make reference to anything else, and theta went from 0 to 2 pi, where we are identifying 0 with 2 pi. Similarly, if we introduce 2 angles here, one is the theta, another one is phi, then we know that we can write z as 1 cosine of theta, and then x can be 1 sine of theta, then cosine of phi, and then y is 1 sine of theta, sine of phi. And now if I add all these things, if I square them, x squared plus y squared plus z squared, then you can verify that by trigonometric identities. This these guys do make 1. So this means we can think of theta and phi as the intrinsic and coordinates on this two-dimensional surface, which we're calling S2, or a two-sphere. So similarly, if I am in 4 dimensions and I have 4 coordinates in 4-dimensional Euclidean space, x1 squared, x2 squared, x3 squared, x4 squared equals to 1, then this should also define for me a higher dimensional sphere, which is a 3-dimensional sphere. Of course, we cannot visualize such a thing, but mathematically, it is possible to describe it. And here, this is basically one description. Another description would be to come up with a analogous, angle for this. So, you can have 2 of these, and you can do theta and then phi and psi. So there'll be 3 angles, and I think it'll be like x4 will be say cosine of theta, and then x3 would be say cosine of theta, and then I think it's what, sine or cosine? Cosine of phi, and then cosine of phi and sine of psi, I think. And yeah, I forget what the exact parameterization are, but you can find this. You can find basically 3 angles, which is going to parameterize the 3-dimensional sphere. So does it make sense, Alpha, why this should be?
Yeah.
Okay. So it's by analogy. Okay. So, all right. Any
Okay.
other questions?
Another thing was like when we were explaining the qubit through the interferometer, interferometer. So it's like a hypothetical question. So in case like a photon can be split into like 2 parts instead of only being reflected or only going through the mirror, that's not a qubit.
Sorry, can you repeat the question again?
So when a photon is like in an interferometer, when a photon is going through a mirror, like it can either be reflected or it can go through the mirror, right? But
Yeah.
in case like it go like instead of a mirror, if we have a beam splitter and it like goes through, it like splits into 2 parts.
So a photon cannot split into 2 parts, right? Physically, it can either go in one direction or another direction. If you make an observation, a photon is not like a classical wave, which splits in its intensity, right? So a photon, what happens to a photon when it goes through a beam splitter is that there is a probability that it can go through or it can get reflected, right? Now, quantum mechanically, that is a superposition of the photon's 2 different states.
Yeah.
Okay? So that's basically, that's why, a beam splitter acts as a way of, creating a superposition of 2 states.
Okay.
So let me just okay, this is a very good question. And so suppose that we have a beam splitter here, and we have a photon coming in, and the photon can go through, say this is path 1, and you can have a detector here, right? And the photon can go here, and suppose there's a mirror here. So this is not a beam splitter, this is just a mirror. and then the photon can go in this direction. And there is another detector here, and this is path 2. So suppose I send one photon in, right? And if if the photon, if this one ticks, then we know that the photon took this path number 2. If this one ticks, then we knew that the photon took path number 1. But the idea about quantum mechanics is that, what if I don't have either of these things? What is the state of the photon? In that case, the state of the photon is going to be a superposition where C1 and C2 will depend on how much silvering this half-silvered mirror is. C1, photon in path 1 plus C2, a photon in path 2. Okay, so this is the quantum mechanical description. And using an interferometer, you can actually create a quantum computer, except that this is known as linear optics, and it can be shown that not all the gates that you need to create a most general quantum computer can be made out of such interferometer. That's a different question, but this is essentially the quantum mechanical description of this process. Okay, but what I'm saying is this is a qubit as well.
Okay.
Because then we can identify this to be 0 and then identify this to be 1.
Yes. Okay. Thank you.
Anything else?
No, that was all my questions.
Okay. So, Ontora, do you have any questions? Okay. All right. So, let's carry on. So, last time I started discussing something like the density matrix, right? So, today I'm going to give you a definition of density matrix. But before that, let's start with a discussion, okay? So let's suppose we have, for example, let's just, go back a little bit and talk about what we discussed last time. So, for example, if we have a system, so classical system, and suppose that we have a classical system in which we have, the system in a thermal bath of a fixed temperature. So what does it mean to have a thermal bath of fixed temperature? Meaning that the temperature of the background will not change. So then we can ask, what is the probability that the system is in the state of energy E? Then the answer was given by Boltzmann, and Boltzmann said that the probability will be proportional to what is known as the Boltzmann factor, which is e to the power minus beta E, where beta is 1 over kBt, where kb is the Boltzmann constant. And what the Boltzmann constant does is that it converts temperature into energy. It gives you an analogous energy. And of course, with the Boltzmann factor, we can normalize probability. And if we normalize the probability, we have to divide it by some constant, some normalization constant, which turns out to be extremely important. In statistical mechanics, this normalization constant is called the partition function. Okay, so this is an example of a probabilistic description of the states of a system. And another one was, so this is known as the canonical ensemble. Okay, the canonical ensemble is applicable when the background temperature is fixed, but the average energy of the particle of the system isn't. So for example, if you have a cup of coffee, sitting in a room, then that's a good, the canonical example is a good description of that, because the room is essentially a thermal bath, so its temperature is going to be constant, but the average energy of the coffee will change over time, and it'll be, described by the canonical ensemble. Another one was that, when the total energy of the system was fixed, and in that case, the probability that the system is in some state is just given by 1 over the number of possible configurations. And of course, the log of the number of possible configuration is what is known as entropy. But this simple, this was called the micro canonical ensemble. And if you did my statistical mechanics course from last semester, I showed how to derive the microcanonical ensemble, how to derive the canonical ensemble from the microcanonical ensemble. Anyway, these are just examples of how probability of a classical system is related to the number of states or the states. Now, we want to do something analogous for a quantum situation. So what situation are we talking about? So the quantum setting that I'm interested in is the following. Now, suppose I have a collection of states of a system. Or we have multiple copies of the system, each of which is given by some state. So let's call this collection S. So S is not a set, it's a collection. We don't want to get bogged down by the mathematical niceties of what is a set. So it has some states, psi 1, psi 2, ... say psi n. Okay? Now, these states don't have to be an orthogonal basis. Okay? These states don't have to form an orthonormal basis. They can be anything. In fact, n can be bigger than the dimension of the Hilbert space, dimension of H. Okay? So, and we don't assume any structure about these states. Okay? We don't assume any special structure or relationship between structure of or relationship between these states. Okay? But the only thing that we assume, and it's a technical assumption, and which we can do without. It just if we don't assume this, we have to implement one more step, which is very easy to do, but we won't do that. So the technical assumption is that all the states are normalized. Okay, all the states are normalized. We can, if they're not normalized, it's very easy to normalize a state. If I give you a state that is not normalized, you normalize it very easily in quantum mechanics. This is not a big deal. Okay, this is a technical assumption, which is not very restrictive. Not restrictive at all, I should say. Okay, now suppose we have a probability distribution P, P1, P2, dot, 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 Pn, where, summation of Pi, I goes from 1 to n is 1, which describes the probability of the occurrence of the states from S. Okay, so what I mean is, so in some setting, suppose one of the states can appear. So the probability that the state psi I is going to appear is Pi. Okay. So essentially, the S is basically a random variable. And the random variable can take the values of the states. And P is the probability distribution, which determines the probability distribution of the random variable. Okay, is that clear?
Yes.
Okay, let me give you some examples so that this makes a bit more concrete. So the concrete examples are something like this. What is the probability of a quantum state to be in a state, quantum system, I should say, to be in a state with energy Em in an environment of temperature T? Well, from statistical mechanics, it's exactly the same thing as we saw before. Quantum statistical mechanics tells us the probability is given by Em kBt divided by some normalization constant that called the partition function. Okay, so it's the same from statistical mechanics. For classical quantum, that's the same thing. Another example, suppose there's a black box which emits spin half particles either in spin up or in spin down state with, say, probability P or 1 minus P. Okay, so this is a situation where the S consists of spin up and spin down, and P consists of small p and 1 minus P. Okay, so these are two situations. So it turns out, to describe such situations in quantum mechanics, you cannot use a wave function. A wave function is not general enough, or a state vector is not general enough to describe such situation. Okay. So in quantum mechanics, the state vector is not general enough to describe such a probabilistic mixture of quantum states. Okay? And maybe in the next class, I will show you an example of how it breaks down. How, if you try, you'll see that it breaks down. Okay, so how are we going to describe this? Such situations are described by the density matrix or the density operator, okay, which is a Hermitian operator. Okay, it's not just Hermitian, it's positive definite, meaning that its eigenvalues are always positive definite. It cannot have negative eigenvalues. Okay, so let's give a definition of the density matrix. Okay, for this system or situation described above, the density matrix is defined to be, so it's an operator, so I'm going to put a hat here, although I might forget that at some point. P1, the outer product between psi1 and psi1, plus P2, the outer product of psi2 and psi2, plus P3, outer product of psi3 and psi3, so on and so forth until Pn, the outer product of psi n with psi. Okay, so this is the definition of the density matrix. So we can employ a summation sign, then the summation will go from I goes from 1 to n, Pi psi I ket psi I bra. Okay. Are you familiar with this object?
Kind of, like, I have to go back and review some stuff, but
Okay, let me remind you what this is. So for a finite dimensional case, we can think of psi as a column matrix. So for example, if I'm looking at the spin up state can be thought of 1, 0, right? And the spin down state is 0, 1. Okay? And then C1, C2, some general state is given by that. So here it would be C1 spin up plus C2 spin down. Okay? So then this thing can be thought of as a row matrix, but it's the Hermitian conjugate of psi. So that means it not only do I have to transpose it, I have to take the complex conjugate of it. Okay, is that clear?
yeah.
So then what is this thing? This is the inner product. This is the usual matrix multiplication. C1, C2 star times C1, C2 C1 mod squared plus C2 mod squared, right? We know that. So, but psi, this thing is the other way around. It's the outer product C1, C2 times C1 star, C2 star. What this means that you take every element of the first matrix, say C1, and you multiply with it all the elements of the other matrix. So you get C1, C1 star, and then C1, C2 star. And then you go do the same C2, C1 star, and then you go C2, C2 star. Then, taking the outer product, you get a matrix, right? So matrix is an operator acting on a two-dimensional Hilbert space. So we can think of this as an operator, right? So because, this thing can act on states. So, which means that if phi was some state, say B1, B2, then this equation is going to read like, this matrix C1 mod squared, C1, C2 star, C2, C1 star, C2 mod squared acting on B1, B2. Okay, this is the meaning of this equation. But this equation also means that we get psi times this complex number, psi phi. So, so if you do this matrix multiplication, you'll get a column matrix, right? And that column matrix is exactly going to be whatever this column matrix was multiplied by this complex number. Okay. So this is a very flexible notation that Dirac formulated for doing linear algebra and quantum mechanics. Okay, so that's why we are defining the density matrix to be as some probabilities multiplying these matrices and then summing over. Okay. Any questions? Okay, so let's look at some the simplest case of a density matrix. So what let's look at the case where our S, our collection of states, has only one state, psi, and the probability distribution has only one entry, which is 1, right? So it's kind of a trivial probability distribution. But what is the density matrix? Rho in that case is this, right? Do you agree?
Yes.
Yeah, from the definition, right? So now, such a state is called it's called a pure state. Okay? If we cannot express a density matrix in this form, even after changing bases, basis, then the state of the system is mixed. So non-pure state are called mixed. Okay, so we have seen a pure state. Let's before we look, shall we look at a mixed state? Okay, so suppose that we have, this is our S. S consists of two states, say plus and say minus, and this is P. P is half and half. Then our density matrix for this is going to be half plus plus. It's a very special density matrix I'm choosing. So, you know, if I look at it as a matrix, then sorry about that. Okay. So if I look at it as a matrix, what should I get? This is going to be in the plus minus basis, this thing, right? And this is going to be this thing. Then what is, can someone tell me what this is? So what
The
is
identity
this?
matrix.
Identity matrix, let's see. So this thing is going to be 1, 0, right? Then this thing is going to be 1, 0, 1, 0. Then first I multiply this thing with both of, I get 1 here, 0 here.
So
Then
1 0
this
0
gives
0.
me, yeah. So it's not the identity matrix, right? So this is going to be 1, 0, 0, 0. And then you can guess what this is going to be. It's going to be 0, 0, 0, 1, right? So then our density matrix is going to be half 1, 0, 0, 0 plus half 0, 0, 0, 1, or half 1, 0, 1, 0. Okay? So what is this saying? It is saying that, you know, this state, which is associated with this guy, has a probability of occurring with probability half. And this state, which is associated with this state, has a probability of occurring also with half. If instead of half and half, I had some other number like P and say Q, where say P plus Q was 1, then the density matrix would be P plus 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 Q minus minus, and then that would be P00Q. Okay? Any questions?
Does the zeros signify plus minus or minus plus, or is the
We will
are
come
they
to what zero signify. So
okay?
far, it's the diagonal elements which are important, which are basically, you know, the probabilities. The zeros will have, the off diagonal elements. We will come to that eventually. Okay. Their interpretation is much more subtle. Okay, let's look at some properties of density matrix. Um, Number one is the trace of the density matrix is always 1. This has to do with the definition, with the probability, the fact that we have normalized probability, right? Right, because if I take the trace of our density matrix, P plus Q has to be 1. But can I prove it? Let's try to prove it. Okay, so this is important to be able to prove simple statements like this, okay? So trace means, what does trace mean in quantum mechanics? When you take a trace of an operator. When you take the trace of an operator, what you're doing is you're taking some basis I. So this is an orthonormal basis, okay? So suppose your dimension is of your Hilbert space is D. So you take such an orthonormal basis, and then what you're doing is you're taking your operator, sandwiching it between the bra and the ket of the basis, and summing over all the basis elements. Okay, so this is what it means, the definition of a trace. Okay, so because this is the definition of a trace, let's see if this definition leads to this result. So now we have to use our explicit expression for rho. So I goes from 1 to D, and this is I. And what was rho? Rho was a sum over J went from 1 to N. There were N states in our collection S, remember? And according to our definition of a density matrix, this is what rho was, right? And then we have to sandwich it between I. Do you understand how we got here? We just introduced the definition of rho here. Okay, so now what I'm going to do is that this is just a number, so I can bring it out. So there's a sum over I goes from 1 to D, and there's a sum over J goes from 1 to N, and P of J, and then I is going to hit psi I, and then psi I bra will hit ket I. Okay. Now what is this? This is some number Ci, and this is some number Ci star. So we can rewrite this as sum over I goes from 1 to D, and sorry, this should be J here. Okay, this index should be J. It's very important to keep track of the indices. Okay, and this index should be also J. Do you understand what I'm doing?
Yes, sir.
Okay. And let's not put a index here. Let's just call this C, and this is C star. Okay, because okay. So now the summation remains like this, and there's Pj. Okay, let's call this a let's call it Ij. Then this is a complex number, and this is its conjugate. That's all I need to know. Then this is Cij whole squared. Okay. Now the thing is that I can now rewrite these things. What is Cij whole squared? This is, as I said, a complex number, which is psi ji, and then psi ji. But this we can rewrite as psi ji I psi j. And here we see this is the projection operator Pi. I don't know if you know about projection operator, but this is also a matrix, an operator. And we have an identity in quantum mechanics, which comes from linear algebra, is that if you have a set of basis states, psi I, and you take this operator and sum over all the basis states from 1 to d, then you get the identity operator acting on that Hilbert space. Okay, so this has a very easy interpretation. All I'm saying is that suppose I have some vector space and I have a vector. If I take the projection of that vector onto each axis, this one, this one, this one, and if I add them up, multiplying by the unit vector along I and j and k, I get this vector back, meaning that that's all that this means. So these guys are projectors. Okay, this one projects down, and this is the unit vector. Anyway, so if you are unfamiliar with this, then we can discuss this, but we can come back to it later and discuss this. But for now, let's assume this is true. So what I'm going to do is that I'm going to now use this over here. What is this? Let me rewrite this again. Let me just take this over here, copy it, and paste it here. Okay. And now what I'm going to do is that I'm going to get rid of all the clutter here. And so I'm going to rewrite this as J, so this, yeah. The J goes from 1 to N, P of J, and then I have psi of J, and then I'm summing over 1 to D, but psi of J came with I, so there's I, and there's I here, I, and I'm going to put this in a bracket, and outside it's psi J. And this I'm claiming is 1, and therefore I get J goes from 1 to N, P of J, psi of J, psi of J, because now this is 1. But what is psi of J, psi of J? That is just 1. So I get as a summation over J from 1 to N of Pj. But because these are probabilities, they sum to 1. And therefore, we have proved that trace of rho is equal to 1. Okay? So I want you to go over this proof again by yourself. So for pure states, that was property number 1. For pure states, rho hat squared is equal to rho hat. And that's very easy to prove. And remember, rho hat is for pure state is just this guy. Then rho hat squared is this times this, but this is just 1, and therefore we get psi, which is rho hat. Equivalently, you could have said pure states rho squared is equal to 1. Okay, and that's very easy to prove because the left-hand side is trace of rho squared is equal to trace of rho, and the trace of rho we have proved is 1. Okay. Now, for mixed states, you can show that the trace of rho hat squared is less than 1, strictly less than 1. Now, this is going to be your homework. You will have to try to prove it using what we know about density matrix so far. Okay, can you do that? Try to do that. I will give you the proof next time.
Yes.
Okay, unfortunately, I have to go. I have a dentist appointment soon. But do we have any questions? We haven't really talked about the papers yet. So I think that's something we should do probably next time. But I think that the technique that I'm giving right now, they are very important. Okay. Isa, thank you, but welcome. But we are about to sign off. But I gave a homework, which is to prove that the density matrix for a mixed state has to satisfy this, that the trace of the density matrix squared must be less than 1. This is your homework.
Okay, sir.
The other thing I will do is that, the stuff that I've taught so far, I will also post lecture notes on that, okay, today. So any questions? Okay, if not, let's meet again next week. But do some homework, do the reading, do the papers. If you have any questions, please ping me in the meantime. Okay. All right.
Thank you.
Okay. I will post this tonight and.